Okay, so as I said, there are 3 steps in coming up with any method. There is an initialization, there's a search direction, where do you which is the next point and how do you choose it, and then you keep iterating till you come to some condition under which you terminate. So here we're going to talk about these 3 steps for the regular falsi. So step number 1 is initialization. So it needs 2 initial guesses that bracket the root, okay, which is the same as bisection. Okay, the search direction actually is interesting. It's actually much better than Newton-Raphson. So let's look at the search direction. Okay, this is how the method differs from bisection essentially. So let's draw f of x again. Okay, let's assume that we chose x1 and x2 such that it brackets the root. So the solution is somewhere between x1 and x2. Now, remember what we did with bisection, we just took the midpoint, like we took x3 would be the average of x1, x2. But for regular Falsi method, what we do is we essentially draw a line connecting the 2 points. So let's say that, well, let's just put this as f of x1, f of x2, and we'll draw a straight line from x1 to x2. And now this point, wherever this line intersects the x-axis, is going to be my new guess. And you can see that the new guess is going to give me a function evaluation f of x3. And now I ask the question, which two, x1 or x2 with x3, which of these bracket the root? And the answer is clearly x1 and x3 bracket the root. So now I continue the process with the same process of drawing a straight line between x1 and x3. Again, look at the intersection and solve for and keep solving for x3 till f of x3 is close to 0. So how do you get the point x3? You require to do some construction. You need to draw a straight line, right? So the coordinate of the point x3, as you can see from the figure, is x3 comma 0. For this point, the coordinate is x2 comma f of x2. And for this point, it is x1 comma f of x1. Okay, now I hope you remember how to write the equation of a straight line. If you have 2 points, or well, 3 points, then you just find the slopes and equate the slopes. So we have f of x2 minus f of x1 divided by x2 minus x1. That's the slope of the line joining the points x1 and x2 equals, and you can pick any other point, say f of x2, and we'll try to connect the line from x3 to x2. So the value of the y coordinate for x2 is 0, right? So I put a 0 there. And then I have x2 minus x3. Okay, so here, because you know x1, you know what x2 is, you also know what f of x1 and f of x2 is, so you can solve for x3. It's super easy to solve for x3, right? I won't spend time doing the manipulation, but you can do it yourself and check the answer I'm going to write down for x3. Okay, so x3 comes out to be x1 f of x2 minus x2 f of x1 divided by f of x2 minus f of x1. Okay, looks a bit more complex than bisection, right? Bisection was just x1 plus x2 divided by 2. This is a bit more complicated. Turns out it has much better convergence properties than bisection, as you'll see. Okay, we got that. And then finally, we have the termination criteria, which is the same as bisection. So you check for tolerance. If the tolerance f of x, absolute value of f of x, or f of x3 is less than whatever you specify, 1e -2 or -3, say, then you stop, or you look up for the maximum iterations. So the final thing here is pre termination is when the absolute value of f of x3 is less than a tolerance, or we'll just put a value of epsilon. Stop. Okay, so suggestion is typically 1e -3, a small number. Or what might happen sometimes is that you just keep trying to compute that f of x3. It never really gets less than 1e -2 or 1e -3, in which case you need to stop, because you need to solutions maybe in real time. So we could also stop if iteration count is greater than max iteration. Okay, so you could specify whatever you want for the max iteration. I would like to keep it like maybe 100, or I don't know, sometimes 1,000. Just really depends on how much time you have to let this do its thing. Okay, so next what we'll do is we'll apply the method, that is the regular falsi, on the same problem and see how better it is compared to bisection, or worse it is. We'll see which way it works out. So the problem here, example. You got that? Okay. Yeah, so here we go, iteration 1. So x1 is 1, x2 is 4. Right? That's the bracket. And of course, when you write code, you want to check if f of x1 times f of x2 is less than 0, because if it is less than 0, then you can just go back here. So f of x1 is here, f of x2 is here. A condition that the root is bracketed with x1, x2 is that the product of those f's, is less than 0, right? You can see it from the figure. F of x1 is positive, f of x2 is negative. If it doesn't bracket the root, let's say that x2 lies here, then f of x1 times f of x2 will be positive, or same if it was on this side. So we always check that, and we'll check that in code. But here, I've given you the guesses such that it actually is satisfying the condition of bracketing the root. So let's compute f of x1. 1 square minus 3 times 1 is -2. And then f of x2 is 4, is 4 square minus 3 times 4 is, it's 4. Okay, so that gets us to x3. So that would be the formula. It's x1 f of x2 minus x2 f of x1 divided by x2 minus f of x1. We just check it. Okay, let's sub in the value. And if you get the answer, let me know. So 1 times -2 sorry, 1 times 4 minus x2 is 4, x1 is minus 2, f of x2 is 4, f of x1 is minus 2. We got the answer. It's 4 plus 6 is 10 divided. So 12 divided by 6, I think, right? It's 2. Did anybody try to get 2? Okay, so then f of x3 is 2 square minus 3 times 2, which is 4 minus 6 is minus 2, right? Yeah. Okay, so now we need to discard one of these, right? So we see that f of x2, which is 4, and f of x3 is negative. So it's 4 times minus 2 is less than 0, which means that x2 and x3 bracket the root. We can discard x1, right? So we'll replace x1 with x3. Okay, so and that basically completes my iteration 1. Iteration 2, x1 is x3, which is 2, and x2 is the same as what it was, 4. So you see that we've gone from a 1 through 4 to 2 to 4. So we have decreased the range. Okay, so now f of x1, which is 2, it's already been computed. F of that's same as f of x3, it's minus 2. F of x2, which is 4, it's also been computed here, it's 4. So now x3 is, I'm going to use this formula here. X1 is 2, f of x2 is 4, x2 is 4, x1, f of x1 is minus 2, then f of x2 is 4, f of x1 is minus 2. So eight plus 6, I think, so 14. And then 4 plus 2 is 6. Seven, 14 divided by 6. It's 2.333. 8 plus 8. 8 plus 8, yeah, 16, my bad. So 2.667. Thanks. So then f of x3 is 2.667 square minus 3 times 2.667. We did that calculation. So minus 0.8881. Okay, so which one should I discard? We have f of x3 is negative, x1 is negative, x2 is positive. So which two would be a negative sign? Well, it's f of x2 times f of x3 is 4 times negative 0.881, and that is less than 0, which means that x2 and x3 bracket the root, I don't care about x1, I can discard x1. So I'll replace x1 with x3, and x3 is 2.667. Okay, so after one iteration, we were here. After two iterations, we are at x1 is 2.667, x2 is 4. So we're getting closer, right? Yeah, question.
What do you mean by bracket the root?
Sure. Bracket the root is if you go here, 1 and 2, x1 and x2. Okay. The red line is the curve. X1, x2 are initial guesses. The curve meets the x-axis at this point. Okay, this is the solution. Okay, so we say initial guess x1, x2 brackets the root because the solution, which I've shown in red, the dot, is between x1, x2. So that's bracketing the root. I always need to ensure that x1, x2, whatever they are, always bracket the root. And I just keep, the way to check that is to check the sign of the product of f of x1 and f of x2. If the sign, so if you take the product, if it's negative, it's always brackets the root, just by the way it is set up. Okay, any other questions? Okay, so, well, this is nice. We got two iterations, but it's a lot of work. And as I said, it's always good to write a code. And we can write a code to check this. So I'm going to basically go to code and then just get the solution till convergence, till it is close to 1 e negative 3. Okay, so last time I had a problem with my code. It was not printing what I really wanted to print. I think I've solved that problem. Okay, I'm just going to open the code which I had earlier, bisection method, main bisection. So okay, so this is the problem I faced. Right, what happens is when I make it print 10 iterations, it just doesn't print all the way down, all the iterations, print 7, 8, 9, 10, 11. Well, one way to fix this, like a sort of unsatisfactory solution, is if you move this up and if you just enter, it just gives you all the iterations. This is like, it shouldn't be the case. It shouldn't do this, right? So that's one way to get it. But clearly, if it's 100 iterations, it will not print. So another way to do this is to write an output text file. You can do it in the following way. So again, you see it disappeared. It's just weird. Okay, so what you can do is you can say diary on. Actually, you can make a, so diary on, diary off is whatever prints in the command window is output of the text file. You could also give it a name. So let's say output.txt. And then you could say here diary off. That way it not print other things which you try to access. So if you run this, it does the same thing, but hopefully when you go here, you see your output.txt, it gives you all the solution. So there's like a workaround. So it's not MATLAB. MATLAB is paid software, but you can live with it. Now, if you want to, the problem with this approach is that if you try to run this, so it ran again, if you go back to output.txt, it actually gives you the first solution, the second solution, doesn't override it. So what you can do, and there's probably more than one way to fix this, is to go here and say delete output.txt and then run this. And then if you go, you just see the first one. So it deletes the file first and then rewrites it. So workaround, but not the best solution, but I guess you can use this in your solution. Okay, so we've got the bisection code working. It converges in 11 iterations. Let's do the second method. But what we did to get this code was we went to ChatGPT, generated the code, and modified it. The thing is that there's only one change you need to make in this file. You just have to change the methodology from c equals a plus b divided by 2. You can see it here. C equals a plus b divided by 2 to whatever that formula is, right? So why not we do that instead of trying to invoke ChatGPT? So what I'm going to do is I'm going to make a copy of, let me just do it this way. We go here, make a copy of that. Let's rename it to regular falsi. And then let's call our driver as, the driver is basically the file which calls it. Okay, and let's modify these files, this one and regular falsi. Okay, so I'll need to well, let me just call this regular falsi. Okay, and that name should actually correspond to the file name I gave here. And then if you want to be super correct about this, you need to write regular falsi. Okay, now this is not going to run regular falsi because I've not made any modifications. Let's just go ahead and do it. So here C is same as x3, and A is x1 and B is x2. So the formula we have for this is C equals so it's x1, which is A, times f of x2. So f of x2 is same as B, minus B times f of A, and then the whole thing divided by f of B minus f of. Okay, so I'll write a note here. X1 is the same as A, x2 is the same as B, and then x3 is same as C here. So you can correct with the notes. Okay, now I could do this, but there's a problem here. This is C, but you see this is not written the way it can be used by regular falsi, because this is not the termination criteria. It's C. C is not A plus B divided by 2. So I'm going to fix that. So what I'll do is here is, so this is just a loop which gets executed. So it basically keeps updating the value of C. So what I'm going to do is I'm going to put a very large value, say 1,000. And then I'm going to say, instead of A plus B divided by 2, I'm going to say C, which is just doing that. You're going to check 1,000 is greater than tolerance, which is a very small number. So it'll invariably go inside. But then once it's inside, it's going to keep getting the new value for C. So it's going to be updated. If you go, we can just try to see if everything is looking good. This is looking good because C is updated. This is fine. Here we have a problem. The root is not this, right? The root is C. So we just change this to root equals C. Yeah, let's hope that it works with C. Okay, so there's an error. Undefined near line 1, column. Line 1. Okay, maybe it's this. Let's try commenting this out. Nope. Anybody see what the problem is? It's saying the error is here. Anybody have a hint? Okay, maybe it's just a memory. Hey. Yes. What could it be? Any idea? Let's see if let me fall back on bisection, see if it works. It should. So I don't know if the error is in this one or it's in something else. So because the way this thing is working on my Windows system. So let me try bisection method. Huh, I have no idea what's going on. Line 1, there's nothing on line 1, column 1. Is there like a mystery symbol, what's that?
Sarah has to do something to name the,
File.
you have, I think it may have to be called root maybe. I don't know.
Root.
I remember getting this a lot of the time, and I had to change the name of the file.
I see. Okay. Interesting. Let me do this. This one works. Let's just check it works. Okay, it works. Let's go here. And then change this name. So calling a new function. Line 12, column 8. Okay, that's better. Line 12, column 8. Let's go to line 12. Line. Line 12, column 8. That's not very helpful. So
Things like this before, I just asked you.
I see.
When you're, like the one here, and it kept saying something about something like the file name or the directory, not line.
I see.
Yeah.
He has some. At underscore what? Add path. Add path. Oh, saying that the path is incorrect. You know what? I can fix it this way. I could. Yeah. So you need to give the whole directory path. You know what? Let me just instead close it, because when I try to run this, it usually tells me change directory. So maybe that will work. So I'm. So main bisection, which is this one. Okay, change directory. So that will do the add path thing. So it worked fine. Okay. So there's a glitch in the software. Okay, so if you look at this, well, actually, I think it cut down iteration 0. So it starts numbering from iteration 0. So if you look here, that's iteration 0. For the way we wrote it down, we consider that iteration 1. That's fine. So it's iteration 1, 2, 3, 4. You can interpret it that way. This took about 8 iterations to converge. So 7, and the bisection method took about, I think it's 11 iterations. We can try it quickly here. We can just comment this out. And we will not delete this, so we can see the output. Okay, so here is both solutions. So the first one is a regular Falsi. It converged in 8 iterations. This one took 11 iterations. So it's clearly regular Falsi is faster. We can also check the solution for, we had 2.6667, right? 0.8889. So that looks right. So first iteration checks with what we have. So I think we are all good. It all works fine. And we did not have to really use ChatGPT. We just took the code and we modified it. So, you know, there are glitches with the software, as you saw. The same code runs when you restart it. It's an Octave bug. You're always welcome to try MATLAB. I just want to stick to a free software. Okay, any questions on this?